Hello everyone, today we'll talk about the problem water bottles. We want to drink as much water as possible. We have some full water bottles at the beginning. And the trick is that if we have num-exchange bottles that we've drunk from, so num-exchange empty water bottles, we can trade them in, and in return we get a single full water bottle that we can drink later. So in essence we drink water from some bottles, we get some empty bottles, we can trade them in for another water bottle, and we want to drink the maximum amount of water. And as an aside, or a first observation, it doesn't really matter what we do. We have to drink all the full bottles, because that of course makes sense. We want to drink as much water as possible. And we want to trade in the bottles whenever possible. So we can think of the order of operations in whatever way we like. The result will always be the same. So of course we can try to simulate this process. And it is a nice exercise, especially trying to make that simulation work quickly for larger and larger number of initial bottles, and for this num exchange, for instance num exchange being equal to 2, so that 2 empty bottles turn into 1 full bottle or equal to something larger. But of course, since this problem is quite similar to yesterday's problem, in that it's again a problem that can be simulated, but also that can have a mathematical solution, I'd like to focus on that latter version, on the mathematical solution to this problem. So the main idea is to look at this exchanging process slightly differently. We know that we can take num-exchange bottles and change them into a single full bottle. But instead what we can think about is that, of course, we take num-exchange bottles, we get a full bottle. So in essence, we have num-exchange bottles that are empty. We select this first bottle and we get rid of num-exchange minus 1 other bottles. And this one becomes full, and we can drink it. Which means that, in essence, in a single step we can get rid of num-exchange minus 1 empty bottles to turn another empty bottle to be full. And of course that all the bottles we can assume at every step are empty, because we can just drink any full bottles at any step that we're at. So, in essence, we can drink, of course, all the bottles that we have, and take all our bottles and exchange num-exchange minus 1 of them for a full bottle. And the only problem here is that we cannot do this exchange of num-exchange minus 1 bottles for a full bottle if we do not have one more bottle. And one way we can get around that is to just set one bottle aside at the beginning, and this will be the bottle that we can imagine will be filled up. So essentially we drink one water bottle, set it aside, and in every step we take num-exchange minus 1 bottles to fill up this bottle and drink it. And this leads to a simple one-liner solution. We drink all the bottles, then we set one bottle aside, and now for every group of num-exchange minus 1 bottles we can get a refill for that one special bottle. And now I'd like to also talk about an interesting aside, which is not necessary to solve this problem, but one that I was wondering about, because it jumped out at me. We know that if we have something like this, we have this, and then this, and so on. So in essence we have a times r squared, and so on. So we have this sum of the form a times r to some power I. And I goes from 0 to something. This is called a geometric series. We can think, of course, about the sum of a geometric series, partial sums of geometric series, and so on. Now the relation of the geometric series to our problem is quite easy to see. Because if we set r to be equal to 1 over the exchange ratio, then we can, and of course a is the number of bottles that we have, then we can drink those a bottles. Then, for every num-exchange bottles, we can turn those empty bottles into full ones and drink them. So we have a divided by exchange bottles. Then, from a divided by exchange, so AR bottles, all of them can also be grouped into groups of exchange and exchange for full bottles, and so on. But of course the difference here is that here we're operating not on integers and not using floor, not rounding down. However, the sum of, for instance, this geometric series, if of course r is less than 1, but it is in our case because this exchange ratio is equal to at least 2, It's an integer here. But if r is less than 1, then we know that this whole thing becomes a divided by 1 minus r. So it becomes a divided by 1 minus 1 over exchange, which is the same thing as, and of course a is equal to our number of bottles, so maybe I write a b instead of a here. This is the same thing as multiplying by exchange, b times exchange divided by exchange minus 1. And when we look at what we've arrived at here, here we have b plus b minus 1 over exchange minus 1. This is the same thing as b times exchange minus 1 plus b minus 1 over whole exchange minus 1. So we arrive at be minus 1 by exchange minus 1. So the question for you is, if I've done some mistakes here, then point them out. Otherwise, can you explain this similarity? And can you explain how we can arrive at this thing, knowing this thing, or thinking along similar lines to this geometric series, which of course doesn't round anything down at any step? So that's an interesting question.